Today we will be learning how the length and tension of a string affects its frequency. For demonstration purposes, we will be using a sonometer, or a tissue box with elastic and pens. Here we have a short white elastic band and a long black elastic band to display how the length of a string affects its pitch. Let's compare how the two sound. We can see that as the length of the string decreases, the pitch increases. This is because the vibrating string is in the first harmonic, and as we decrease the length of the string, the wavelength decreases as well. We know that the frequency and wavelength are inversely proportional in this medium, since the speed is the same. Therefore, as the length of the string decreases, the pitch or the frequency increases. This is because the higher the frequency of a string, the greater its tension. A vibrating string can vibrate in multiple harmonics. We can use the formula frequency 2 over frequency 1 equals length 1 over length 2 when there is both a constant tension and a constant speed. It can be used to find the length of the string needed to produce different frequencies, or notes. The ratio F2 over F1 defines the musical interval between two frequencies. Let's do an example problem. If we have a string with an original length of 0.35 meters and a frequency of 450 Hz, and we want the new frequency to be 600 Hz, what length of the string is desired? In our pictorial representation, we label all of our given information directly from the question with proper units and state that we must find length 2 in meters. To find L2, we can use the equation F2 over F1 equals L1 over L2 by simply rearranging the formula to isolate L2, plugging in our numbers with proper units to find that L2 is 0.26 meters. Therefore, the length of the new string is 0.26 meters. Let's try another one. A spring 4.7 meters long vibrates with a frequency of 3.7 Hz in its fundamental mode, or its first harmonic. You hold the spring down so only a 2.1 meter section can vibrate. What is the natural frequency of this section? Again, we label all of our given information directly from the question with proper units and state that we must find F2 in Hertz. In our mathematical representation, we state that we must find frequency 2 using F2 over F1 equals L1 over L2. This time we rearrange the formula to isolate F2. Once we plug in our numbers, we find that the resulting F2 is 8.3 Hz. Therefore, the natural frequency of the 2.1 meter section is 8.3 Hz. Isn't this easy? Today we found that a shorter string will vibrate in a higher frequency with a lower wavelength, and so a longer string will vibrate in a lower frequency with a higher wavelength. A vibrating string can do this in multiple harmonics. We can use the equation F2 over F1 equals L1 over L2 to find the different lengths of string needed to produce different frequencies. Remember that this formula assumes a constant tension and therefore a constant speed. We hope you learned something from our lesson today. Thanks for watching.